I think we have essentially all the speakers and everyone is accounted for, so I think we can start this event. So thanks everyone for joining us in Rio. Thanks a lot for Felipe, who essentially funded this whole conference. So I have to do, yeah. Very well. Well, also, I will do the thanks in advance for the staff at IMPA, who is always very helpful. I think Sueli or Leticia and Carolina are not here, but this was a very easy to organize conference, as none of us was in Rio, and this was all done by email, so and everything ran sort of smoothly. So the idea was, I think a year ago I was here at IMPA visiting Felipe, and one day we were talking about organizing something that vaguely had the Fourier analysis topic in the back, and sort of reached out to other kind of connected areas like approximation theory, problems in discrete optimization. So I think we have a very nice crowd. The only thing we had in share when I was inviting speakers was that we wanted people who were going to talk about interesting stuff and that were good speakers. And I think we have a very good list. I think everyone will be happy. And we hope that this will be the first edition. This is why we gave a number at the end of the name. Let's see if at the end of the week we will decide something about the next one. But so, some announcements. Okay, you guys, I think everyone received an email with some instructions about general things in Rio and about the venue. So we have a restaurant downstairs that probably everyone will go for lunch. So the price is 28 reais, which I don't know how much is in euros or dollars right now, but I'm sure you can figure it out. So it's pretty easy to figure out how the system works. Essentially, you can get anything that is on the buffet area, and then the protein, you go and choose one. There are vegetarian options and for those who, and also gluten-free ones. Great. I think you received instructions for the internet. There is EduRun, but there is also the password somewhere. For those who are receiving financial support, you will get an email, either today or tomorrow maybe, because Felipe has to do some administrative stuff before. Unfortunately, his flight was delayed. He couldn't arrive last week as originally intended. And there will be a conference dinner on Wednesday. We will be revealing more details along the day. But we need to do a head count first to discover how much it's going to cost. But yeah. So, did I forget anything? I don't think so. If we remember, this will be reviewed along the week. So I think without further delay, we can have our very first mini course by Stefan Steinerberger. We'll be talking about some open problems in Fourier analysis. Thanks, Stefan.
Let's see. Does it work? You hear me? Okay. Oh, Hio continuo lindo. Yes, I will not embarrass myself any further, but it's a great pleasure to be at IMPA. In fact, it's so great. I've tried before more than once. So this is my very first time at IMPA, but in 2018, I tried to get in, and I couldn't. You see from the face, this was December 2018, Christmas break. They said, sorry, it's closed, you can't get in. I said, I just want to see it. I was a tourist, I was visiting. No. And you can tell from my face, right? Okay. 3 years later, Colloquio Brasileiro, completely online. Again. So, but now, third time is the charm. I'm very happy to finally be here. It's a great pleasure. Very much, I really worked for this, So, finally. So the idea of this mini course is a bit different, because usually you're supposed to talk about results, and I will talk about bad results and failed attempts. But the whole point is actually kind of to talk about problems that should not be out of reach. Okay, so I'm going to have a collection of 16 problems, and the whole point of these problems is I don't think that they're impossible. Maybe one or two. If you buy me a caipirinha, I will tell you which ones. But assume that, they should all be within reach, and what they also have in common is usually they're representative of an entire class of problems that I think might be worth investigating, and they're also problems that I think could benefit from the right idea at the right time. And I tried the ideas I had, but there are many smart people in this room with many smart ideas, so I think there's actually room to do something. And I've never done this, and in 2 years I will know whether it was a success or not, but it may well be a success. It may also not be, but okay, we'll see. That's the plan. But you see the emphasis, I put it in italics. Progress here should be possible. Okay, and I've got a vague plan. I've got a vague plan that probably I will not follow. I'll see how far I get, but we'll see. Okay. And feel free to interrupt me with questions or comments or remarks. This is supposed to be fun and casual and relaxing, but I want these solved, okay? Don't be mistaken about that. I want solutions. And I'm going to start with this one, and I want it solved. You see in the footnote, you have 5 years, okay? You have 5 to 6 years to solve this, because then it's 100 years. That's too long. This problem is well known in additive combinatorics, but it's a Fourier analysis problem. And you get to the state of the art using nothing but fairly elementary sines and cosines, but Fourier analysts don't know about the problem. So now I'm going to tell you. And this is in fact, so Erdős says it's his first serious conjecture that he ever had. And it's going to sound like additive combinatorics, but I'm going to tell you right now, it's convolution. We all know what convolution is, okay? It's convolution. So the question is the following. There exist sets of integers with the following property. If I pick a subset and sum up all the elements, the sum uniquely identifies the subset. And the easiest example is powers of 2, right? If I take some powers of 2 and I sum them up and I tell you the result, you can immediately tell me what the powers of 2 are, like which ones I used. This is what's called binary expansion, right? Easy. So the question is very, very, very simple. The question is, are powers of 2 kind of extremal in this? It's clear. So, okay, Fourier analysis conferences, right? People know what lacunary sequences are. Like if I take something that's exponentially growing, right? Like 10 to the n, will also have this property, of course. But the question is 2 to the n kind of extremal? Is this the most compact way to get a set like this? So the more precise question is the following. Is it true that there exists a universal constant such that the largest element in your set has to be roughly 2 to the n? That's the question. Any clarification questions? No? A very, very simple question, very elegant, very pretty. Now, powers of 2 tell you, the constant can't be 1, it can be at most 1/2. And the other thing that's nice about this, there's a nice sort of tensor construction built in. So if you have a good set with a small constant c, you can do the following. You take the set, you double every element, and you add 1. And then you inherit the constant in the next step. You get exactly the same constant, because if I now take a sum, so let's see whether the pointer works. Yeah, perfect. If I take any sum of this, if it's even or odd, it tells you whether 1 was used. Then you disregard 1 or not. I mean, you subtract it or don't subtract it, depending on what it's used. You divide by 2, and then the remaining sum uniquely identifies the subset, and you're good. Okay, so that is the problem. Now, it turns out there is some results from, this is our oldest problem. This is a result from 1968, and the result shows that the powers of 2 are not optimal. So it turns out there is an example where the constant is less than 1/4, and it's an explicitly given recursive sequence. I'm not going to give you the details of this, but you can check it out. It's not too complicated. And there was some improvement over the years. So this is the constant from the original letter. And there's some further improvements, and now the current state of the art is roughly 0.22. Now, what's funny about this problem is it's not clear to me the conjecture is true. It's not clear. It's clear in some sense. I think what's misleading about the conjecture is like the powers of 2 are an absolutely amazing construction, and it's an infinite sequence that works for every n, right? If you pick n is 50, you take the first 50 powers of 2, clearly they work very well. So if you take an infinite sequence that's uniformly good at each step, maybe you have to have powers of 2 or something like it. But if you just pick n is 50 and you want 50 numbers, it's not clear to me it's true. Not clear at all. Okay, let me tell you about the trivial lower bound. The trivial lower bound gets you almost there. If I have n elements, I have 2 to the n subsets, I have 2 to the n sums. These sums all have to be different, which means the largest one of these sums is at least 2 to the n. That's it. The largest one is at least 2 to the n, and of course, if I have n elements, I mean, the largest number I can get is at most n times the largest element. You combine these two facts, you get 2 to the n of n. That you get for free. Completely trivial. Now, it turns out the best current bound is this. It's 2 to the n over square root of n, and I already told you it's convolution, and what this is an L2 argument, and I'm going to show you the L2 argument. And Moser doesn't even call it an L2 argument. I'll tell you the phrasing that he used, but this is what we know. And this has not been improved for 7 years. And when you see the proof, you'll be like, oh wow, this is trivial, I can improve it in one afternoon, and then you realize, oh, well, maybe it wasn't trivial for me. I fell into this trap, right? I was like, oh, this is easy. So let me give you the proof. The proof is convolution. So if you like, I'll give you the probability version and then we see what happens, but you have these magic numbers. Wow, this is amazing, Josh. This is really nice. You know, come try this later. This is, wow, okay. So the idea is the following. And this is not entirely obvious to see, but the trick is the following. You can write every subset, so a 1 plus a 3, I can write as the sum of all the elements minus twice the elements that did not contain a plus 1. This is middle school. It turns out the algebra works out. So that's not too terrible. But what this tells you is that if you look at the random walk, where you take steps plus minus a 1, all the plus minus 1 configurations are uniquely reconstructable. So it's not just that you can reconstruct the subsets, you can actually reconstruct all sign combinations. So what this means is if you have this random variable where each sign is chosen uniformly at random, Rademacher, Bernoulli, 1/2, you get a random walk on the real line, and the random walk looks as follows. It assumes 2 to the n different values, and each value is assumed with likelihood 1 over 2 to the n. So it's as a probability distribution, it's completely flat. I mean, okay, it assumes integer values, right? So there's little Diracs here maybe. But if I zoom out, it's a very flat kind of distribution. Something like this. We don't quite know what it looks like, but no value is particularly likely. And now the proof, now the proof is just compute the variance, which is L2. So you look at the L2 norm of this, and so X is, I really like this board. This is amazing. So this is a random walk, right? And now the expected value of it is 0, because plus and minus 1 are equally likely. So in order to compute the variance, I compute x squared. And what happens is all cross terms vanish. What's left are the diagonal terms, and you're left over with a very, very simple expression, which is this. This is the variance. But now if I tell you, we know that no value is particularly likely. So how small can the variance be? Well, best possible case is you have one value at plus 1 and one value at minus 1. But no value is particularly likely. So the maximum likelihood that sits here is 1 over 2 to the n. And here too. But a probability variable sums up to 1. Okay, well, maybe minus 2 is also here. Turns out minus 2 can't be here. They have to be 2 separated, but that's a constant. So maybe that's happening too. But it turns out if you do this, you realize you have to go out at least to minus 2 to the n minus 1. So the variance, if you compute it, is at least 4 to the n, roughly. Because mean is 0. you spread over at least the scale 4 to the n. And now you're done, right? Because now you know that this is, or at least, constant times 4 to the n. And again, we use the trivial upper bound. We say it's n times the largest element. And that gives Moser's result. That's Moser. That's 1950s. That's the state of the art. It's not the state of the art at the level of a constant, but it's the state of the art at the rate. And from a Fourier analysis perspective, I think that maybe I have that on the next. Okay, so there has been some improvement on the constant over the years. So these three all give the same value, and in some sense, they're all the same proof. So the problem is, Elkies and Gleason never published their proof, so no one knows what it is, but I assume it's mine, or mine is theirs. Pretty sure about this. Dubrow, Fox, and Xu, they have two proofs, but essentially they boil down to the central limit theorem, and the central limit theorem boils down to Fourier analysis. So I think it's also maybe the same proof. And I'll show you the proof. I mean, the proof's not complicated. Okay, but this is the problem. This is the first problem. This is Erdős's very first conjecture. Now you know the state of the art. The state of the art is on the blackboard, up to the constant. The approach that has, I think, not yet been tried, or not tried enough, is Fourier analysis. So I don't know Fourier analysts who have worked on this. Fourier analysis comes out in the existing arguments. So it turns out there is a very nice reformulation. The reformulation is not very complicated to attain, because when you know that this is true, right? When you know that this random variable assumes integer values that are separated, you can convolve this with a nice bump function and compute the L2 norm, and everything simplifies in exactly the correct way. You'll see this on a future slide, but this is a completely elementary Fourier analytic reformulation. You see, it's just a product of cosines. And the question is, can a product of cosines be very, very decorrelated? That's kind of the question. So what's pretty about this also, it's a product of many cosines. So you really have exponential decay in a sense, but they're all aligned at 0. At 0, all the cosines are 1. And it turns out if you just use the fact that all the cosines look like this in the beginning, and you do a Taylor expansion, you already recover Moser's result. So a trivial Taylor expansion of this fact in the origin gives you Moser. That's the state of the art. So what about points far away, right? And then it becomes a question of integers having to kind of line up, frequencies having to line up, but it's a Fourier analysis question. Good. Just because I promised the convolution, here's the convolution, right? Really what you have is you have a Dirac at plus and minus AI. You convolve those, that gives you a probability distribution about which you know it's extremely flat. That's it. Questions, comments? Everybody happy? Okay. In particular, you know that the convolution of these Dirac measures is the sum of 2 to the n Dirac measures that have equal weight. And you get fairly quickly that they are also gapped. So this surely must be exploitable a little bit more. Okay. So there's some room to do. But now you know now you're at the frontier of knowledge. Now you know what everybody else knows. And it was pretty quick. Right, this I already kind of drew. Right, this is the argument I'm trying. Sorry, I got jumbled up in the order. You do a local like Taylor expansion around the origin, you already get Moser. For emphasis again. Good. I want to emphasize, so I mentioned the central limit theorem. So there's one very interesting byproduct, which is, I haven't been able to use it, but if the largest element is very small, if the conjecture is false, then you get extremely good rates in the central limit theorem when it comes to this random variable. So I've already told you, this random variable is extremely benign. It's 2 to the n Diracs with weight 1 over 2 to the n. But if you zoom out at a coarser scale and you ask how many Diracs are in here, you start seeing very pretty pictures. So this is actually, I computed this for the first 22 elements of the Conway-Guy sequence. And I zoomed out. So it is, in fact, a flat union of Diracs. or flat sum of Diracs. But if you zoom out at a coarser scale, the density starts approaching a Gaussian, which is interesting in itself. And the thing to use to get the current state-of-the-art result is that you know that get the density of a Gaussian at 0, and it can't be too dense, because they're too separated. You're done. That's it. That's the state-of-the-art. Okay, next problem. That's the pace, right? We have 16 problems. We got no time to waste. And I want solutions too. So this one's going to be short because this one's probably hard. But it's extremely annoyingly open. So the question is very simple. You're given a whole bunch of cosines. How many roots is this function going to have? That's it. It's a sum of cosines. If you sum up 1,000,000 cosines, how many roots is it going to have? And the coefficients are all 1, right? So there's no complications here. It's just you only choose the frequency. The frequency are some integers. So Littlewood himself thought that the best case is probably the following. Littlewood said, high frequencies are bad because high frequencies go up and down. So you want to have low frequencies, so probably you want to take the first n integers. If you take the first n integers, it gives you the Dirichlet kernel. You know everything about the Dirichlet kernel, and the answer is roughly n, where n is the cardinality of the set here. The trivial bound is 2. So Littlewood thought it would be the Dirichlet kernel. This was actually disproven, so there have been a sequence of improvements that got it down to 2/3. The thing I want to emphasize is the lower bound. There has recently been an exponential improvement in the lower bound from 3 logs to 2 logs. So if I add 10 trillion cosines, does it have to have at least 30 roots? It should. Why don't we know? So I spent a lot of time on these problems without any success. I mean, almost negative success. I forgot more than I learned while thinking about this. But this is a very cool problem. There is a little bit of a warning. So it turns out it's kind of relevant that the constant is 1, because you can do the following. You can pick a 2 here, and then these numbers are just 0, 1, and, they're just, 0, 1, and -1. So they're not attaining many different values, but it's 0, 1, and -1. And these functions look like this. And you kind of see the picture. Oops, let me go back. So you see the picture, you see what's happening. It starts oscillating more and more. There's a limit, and this thing only has 2 roots, 1 here and 1 here. So that's a little bit scary, the fact that this may make a difference, but okay. So that's a really great problem. Littlewood's cosine problem. A fair warning, it might be very difficult, but it also hasn't been looked at by enough people. Because it's really, log is not, well, maybe it's log, who knows. Anyway, so this one's short, and since I'm talking about cosine problems, I will do a 1-slide problem, so that's number 3. This one is also open since the 40s, I think. And the question is about the same framework. We have a sum of cosines, maybe n different cosines. Is the sum going to be negative somewhere? Well, of course, right? Mean value is 0. So it's going to be negative somewhere. How negative does it have to be? And the problem is, well, here's an example, right? I mean, this is a set A, and you see, of course, they're all 1 in 0, so they all add up in the origin. But then it is not inconceivable that they kind of cancel each other out, and they never become very, very negative. So, and this is, so there was some progress in the 80s, 90s, early 2000s, but there hasn't been any progress in, I think, 20 years. And, this is not yet polynomial, right? What people expect is roughly n to the 1/2, like the number of elements to the 1/2, like the estimate you expect from sort of L2 should be sharp, but like square root n. Okay. 2 quick problems. Fair warning, they might be difficult. On the other hand, they haven't been explored in a while. There have been advances in harmonic analysis in the last 20 years. There has been a fusion with other fields. Maybe it's time. I tried. I tried. I couldn't do it, but so what? Okay. Next one. So this is a funny one. okay, this is, I did this in LS Correal, and people were amazed by my computational powers. I'm going to do a magic trick, okay? Don't spoil it if you've seen me do the magic trick before. I'm actually going to compute in my head the Hardy-Littlewood maximal function. How about that? I'll do it for a sine or a cosine, you know, not labeling anything. So if you just take a standard sine or a standard cosine and you compute the Hardy-Littlewood maximal function, what do you get? And the answer is, it's funny. You get something very interesting, but no one knows about this because no one ever computes the Hardy-Littlewood maximal function. It's a tool, right? You teach it, you prove the L infinity, L1 infinity, right? Constant 3, basic coverage covering, right? But no one's actually ever computed it. And I can tell you for the following reason. No one's ever computed this because I cannot do the following. What's the value of the Hardy-Littlewood maximal function here? It turns out you can kind of guess, right? Because you have to take an average. But here it's concave. So the average is going to be smaller than the point value. And then you immediately hit the negative region. And, so it turns out the value is actually this. So it turns out here the maximal function is exactly this. Now, question, what's the Hardy-Littlewood maximal? So how about I label this 0? So I'm doing the sine. Here is pi. Here is 2 pi. So what's your favorite number between 0 and pi? Pi and 2 pi. 4, right, perfect. It turns out the length of the interval, I mean, now you can tell, you can improve a little bit. The length of the interval is 8.9. Dot, dot, dot. How did I do this so quickly in my head? Unbelievable. Well, it turns out, I'll show on the next slide. So the question I want to raise here is actually, if you look at the Hardy-Littlewood maximal function, how about we ignore function values? How about we ignore what the value of m of f is? And we instead look at the radius at which the maximum is attained. When you compute it, that's actually a natural object. And here's the example, so you can do this in closed form. It turns out the optimal radii is either 0 or it's 4.49, which is, and twice that is roughly 8.9. So it turns out the length of the maximum interval when you're negative does not depend on where you are. It's always the same. Now you can see why, right? Because when you do the computation, I mean, this decouples. So this function has a maximum value at 0, and it has a minimum value at exactly this number 4.49. It's not magical that it's true. It's kind of magical that no one knows. And I think there's some interesting results attached to this. Questions before I continue? So this was actually discovered while preparing a lecture. I was preparing a lecture, you know, teaching undergraduate harmonic analysis, and you teach the Hardy-Littlewood maximal function, and I wanted to do an example. And what's the easiest function? It's a sine. And then I got this result, and I'm like, this is odd. So, okay. In fact, you can get a little bit more. It tells you that what happens is something very funny. The maximum and the minimum average are both attained at 0 and 4.49 no matter where you are. There's an invariant way that doesn't do a sign distinguishing. Okay, so it turns out you can prove something like this. So I worked very hard to prove this. I'll tell you why I worked hard to prove it, but the statement is the following. The statement says we have some periodic function with some regularity, and probably you can lower the regularity. The regularity is not the issue. What you do is you have an averaging operator. So you average at a fixed point x, and you average over a scale r. That's what you do. And I'm telling you that something fun is happening. What I'm telling you is that this averaging function, as a function of r, has a critical point always in the same space, independently of what x is. Which is exactly the situation that we have here if we have a sine. If we have a sine, and I average here, where it's positive, it turns out at 4.49, if I average over this scale, I get a minimum, which is also a critical point. So that's the invariant formulation. So the sine is an example of a function that has this property. And it turns out if you do have this property, then you're the sine. So that was kind of I expected this to have a trivial proof. It still may have a trivial proof. I tried a long time to find the trivial proof. I'll show you the proof and what it means in terms of delayed differential equations, which was a big surprise. What's the obvious thing you do? The obvious thing you do is you just write down the condition. The condition says this, right? I have an averaging operator as a function of R. It has a critical point, which means the derivative is 0. So how about I differentiate it and I set it equals 0? And what you get is you get this. And what this is it's a delayed differential equation, right? It looks like a differential equation, but the value at x plus gamma depends at the value of x minus gamma. So these type of, they're like ODEs with memory. And what happens is you have to prescribe information over an interval of, so you have arbitrary initial conditions here. Not my best function, but once you're here, you can continue, you can start using the equation and you get solutions. So delayed differential equations are a bit like ordinary differential equations, but you have a lot more freedom in the initial segment. So one way of phrasing the statement is, among all the uncountably many initial conditions, you only get periodic solutions if you start in a four-dimensional subspace, which I thought was kind of weird. And I'll show you the proof, because the proof is fun. You just differentiate. You expand in Fourier series, you differentiate, and you realize you get this very pretty equation. Now, this is a number depending only on gamma and k. Here you've got a frequency. The statement is this Fourier series gets completely annihilated. Now, how do I annihilate a Fourier series? Well, either these coefficients are both 0, or this coefficient is 0. No other choice, right? You apply Plancherel, and you say it's a sum of squares, and the sum of squares is 0. Sum of squares is only 0 if everything's 0. So what you have to prove is you have to prove that for any gamma, this object can only vanish for one integer. Because if it vanishes for two integers, you have a problem, because then you could put non-trivial frequencies there, they get annihilated, the theorem is false. So it can only vanish at a single integer, and this, if you rewrite it, boils down to the following. It says that any two positive fixed points of the tangent are linearly independent over Q. So I see people making faces. I made the same face. So it turns out when you look for this result, you don't really find it. But you find, and this is why it took me a long time, you find a hint in the exercise section of chapter 9 of a textbook on Galois theory. Now, I don't know any Galois theory. And I had to read all these chapters to be able to do the exercise in chapter 9. And I was cursing for 3 weeks, every page is agony, but then it turns out it's not too hard if you know how to do it. And I wrote it up in the end in a way that people don't have to struggle the way I struggled. Should have paid attention in undergrad, but here we are. So this is kind of funny, right? I mean, also it's completely algebraic, it's completely not robust. It's exactly the proof you don't want, right? So here's my question. What can you tell me about this maximum radius function, right? You're given a function on the real line, we can keep it one-dimensional. Assume anything you want about your function, C infinity, bounded, periodic, whatever you want. And you actually compute the Hardy-Littlewood maximal function at each point. Well, there's a little bit of a question of how it's defined via a soup, so maybe if it's interval 0, do you allow 0? Sure, why not, right? But the question is very simple. Do you see a lot of different maximal radii? Well, the answer is not necessarily, because for the sine you only see 2. But I think this has to be a freak accident of nature, right? I mean, this cannot possibly be generic. So I think there's a very obvious question here. The question is, if you have a function that's not the sine, does the maximum radius function assume infinitely many values? Or, does it at least assume 7 values? I don't know. Next question. I would believe that generic it's infinitely many values and there's some Hausdorff dimension of the values, but I have absolutely no idea. It's actually kind of a hard question, I think. It's not quite clear what to do, but I find it very interesting. There's almost nothing on this, so there are 2 papers by Farouk Temur who are exactly about this problem. I mean, not exactly. He does it on L1 of the integers, so little L1 on the integers. It's not quite the same question. He calls it the frequency function. The 2 papers are referenced here. And he's proving versions of, I give you an L1 function, then it turns out you can't, this maximum frequency function, as he calls it, cannot grow slower than linearly everywhere, which kind of, the motivation would be the following, right? If it's an L1 function, you have a bump somewhere. If the bump is here, and I'll draw this, how about that? So I think L1 is a little bit different here. Maybe L infinity would be the one that's not scaled. So L1, what does an L1 function look like? Well, this, right? Kind of. So if I'm very far away, what's the maximum radius function going to be like? It's going to be roughly the distance to the bump, which means you expect the maximum radius function to grow like x. And he's proving this in a sense. He says if you the little c, that the constant here is just a little bit larger than 1, if you just increase it a little bit, that doesn't happen. So you're not much shorter than x most of the time. That's clearly an L1 statement. It's not true in L infinity at all. Or maybe it's still true, but for different reasons. So there's something to be done here. He also has versions about how big is the set where the maximum radius function is 0, which corresponds to some sort of local concavity, local maximum. And he says, yes, it's actually possible that you have a large set of zeros. So there's constructions like this. But these two papers are the only papers I know that deal with the question. I think it's wide open. Okay.
So, Stefan,
yes?
is that, do you have anything of the non-centered version of this?
Do I have any version, a non-centered version of this? I do not. I have absolutely nothing. I've told you everything I know. I agree. There's a lot of interesting questions here. Other questions? Okay. So I'll do this one because I find it so insanely offensive. This is a quick one. Some integers can be written as the sum of two squares. Yes, we agree. This is not a very controversial statement. Now it turns out there's a very nice result by Landau, and Landau shows asymptotically the numbers of below x that can be written as the sum of two squares are roughly x over square root log x. Okay, so this tells us the average gap between two such numbers at scale n is roughly square root log n. That's rephrasing Landau, right? If the asymptotic density is this, the average gap size is roughly square root log n. And it turns out the question is now, how big can the gap be? This is the average size is square root log n. Now let's look a little bit. This is the sequence of sums of two squares. Looks almost linear because you can't see the square root of the log, right? It's a little bit superlinear. Here's the sequence of gaps. Okay, pretty nice, pretty friendly. Let me renormalize by dividing by the log. Yeah, could be bounded, right? Maybe it's not bounded, but it's a log of. The usual heuristic is like, it's a square root of a log, right? Square root of a log's pretty tiny. Now, it should be semi-random without making this precise. If it's semi-random without making it precise, how much do you lose in the central limit theorem? Another square root of a log. So maybe log's the right answer. Maybe log squared, okay? Here's the best upper bound. And one of the reasons to talk about it is because he passed away very recently. The best upper bound is a polynomial power. So even though the truth is logarithmic, we only have a polynomial result, a power of roughly n to the 1/4. Okay, now you're going to say, well, that's life. Sometimes things are difficult. The thing that's really amazing about this result is the proof is one line. Want to see the line? There's the line. You take the largest square, smaller than n, and then the smallest one that gets you just above. In equations, that's the line. So this is an integer. This is an integer. This is a sum of two squares. It's bigger than n, and it's smaller than this. That's it. That's the proof. This proof has, well, I find it, this is ripe for improvement, I would say. What's funny about this is not even the constant's been improved. There is one paper that removes the 1. There's another paper that turns it into a -1 and says turning it into a -2 with current technology would not work. Okay, that's the level. As square root 8 is, I mean, and the reason I think it's appropriate to present, besides that, I mean, come on, like, it's one line, right? One reason to talk about it here is, of course, we're talking about a purely geometric statement in the plane, right? What we're talking about is, are there wide annuli centered in the origin that don't contain any lattice points? That's the question. I mean, that's a pure Fourier analysis question, right? So you take a Poisson summation formula, then you look at the Bessel functions, then you don't know what to do. Well, that's my story. But I feel it's a good problem to present. Good. Questions on that? Ideas, suggestions, quick solutions? Okay, you have another 20 minutes for the quick solution. Good. So I think I have until 11. Or is it 50 minutes, 50 plus 10? 50 plus 10. Okay, maybe I won't finish all of this. So this is a very fun story that kept getting funnier and funnier, and now I'm going to tell you about it, and I'm going to share beautiful pictures of beautiful people who are in the audience. Come on, it's a nice picture. It's a nice picture. So we had some fun problems involving Hermite functions, and the motivation was, so there's a long motivation, maybe mentioning this, no? Okay, the hand-wavy explanation is quantum mechanics should be local, it should be local in a neighborhood, far away things should be random, but sometimes this is violated. Okay, that's the vague motivation, but it can be, so this is the appropriate Einstein quote. Okay, quantum mechanics, for the purpose of the next 5 minutes, are eigenfunctions of the harmonic oscillator, the eigenfunction of the harmonic oscillator, Hermite functions. Hermite functions are old friends because they're also eigenfunctions of the Fourier transform. So these are, and here you see what they look like, and they're really nice. And the question is essentially, if I take two different points in space and I look at the sign of the value of the Hermite functions. So you pick, I don't know, 4, right? Someone likes pi and 4, right? From quantum mechanics perspective, they're far away. So I have pi over here, I have 4 here. These are very far away. As the frequency increases, you have, more and more oscillations, and, the behavior in these 2 points should essentially decouple. And it turns out that's usually true, but not always. And one way to ask whether the behavior decouples is you look at the value of the first eigenfunction, the first Hermite function in both points, and say, are they both positive, are they both negative, or do they have a mixed sign? Then you look at the second one, you look at the third one, you look at the fourth one, and you say, are the signs correlated or uncorrelated? And of course, they should be uncorrelated. And it turns out that's usually true. It's true for almost all, in the Lebesgue sense, pairs of points. So if you pick 2 at random, yes, they're uncorrelated. Or at least, they're uncorrelated, that's correct. But it turns out, for example, if you take 1 and 5, they're actually positively correlated. So if the Hermite function is positive in 1, it's more likely to be positive in 5 than negative. Which is a bit strange, right?
Isn't this somehow to do with, so these are orthogonal polynomials, right?
These are orthogonal polynomials.
They have some sign changing.
There's rigidity you get from the harmonic polynomial, but here we let the frequency goes up. So then it should kind of decouple. So if you had very low frequencies, yes, then it's extremely rigid, and the nth harmonic polynomial has n roots, so n minus 1. But here we let n go to infinity, so to some extent the roots go to infinity as well. So that's not what's causing it. Yes?
I don't understand. What do you mean by correlate or decorrelate in this case?
What I mean is the following. You pick x is 1, and you pick x is 5, and you write down the signs for case 1. Okay, I'm going to lie because I don't. In case. So that here's positive, here's negative, and.
Okay, and then you average and see which one.
That's right.
Okay, yeah, so it's in K. Okay.
The average is in K.
You average over rows.
That's right. So somehow what happens is a particle at 1 and a particle at 5, they talk to each other via sort of magic long-distance correlations, which is kind of funny. And we'll come back to this, and it can be made rigorous. And so Diogo, Felipe, and I have a paper on this. And there is one lemma. And the lemma is very, very simple, and it's very cute, and it's very fun. And I think Diogo has a magic formula that you can find in the paper that even resolves this. It's a nice infinite series. So the question is the following. If you take two cosines, so here's a cosine and here's another cosine, how large is the set on 0 to pi where they have the same sign? Well, it could be very large, because if you take the same cosine twice, it's 1. How small can it be? Could it be that they always have this? Well, they have the same sign at 0 by default, because it's a cosine, it's 1 at 0. But maybe you could arrange the frequencies in some terrible way so that they always kind of alternating. And the answer is no, you cannot. At least a third of the interval, they have to have the same sign. And the extremal case is if one is 3 times the value of the other. That's it. It's kind of a cute result. Here's an example of the extremal case. So you see two cosines, one in green, one in orange, and you see the region in blue where they have the same sign, and you see that's a third of the interval. Okay. Nothing too complicated, nothing too surprising. So what happens about this, what's kind of funny about this problem is, okay, maybe I should try this general version. So if A and B are very, very large and they don't talk to each other at all, they're sort of large random numbers, the answer should be a half. And that leads to, so this is kind of an example of this, and that becomes very useful. So here's the general question that I would very much like an answer to. What happens to the general case? And I first thought this would be kind of an easy problem. In fact, this started out as undergrad research. I gave this to undergrads, and I said, here's the paper with Diogo and Felipe, read the proof, and then generalize it, find out what the answer is, and generalize. Because it's kind of, it's a nice proof, and you can kind of generalize it. They learn a little bit of Fourier analysis without realizing. So that's the question. Does anyone have an immediate answer on how to do it? It's a funny question. Okay. So I'm going to write the answer as f of n. So if you have two cosines, at least a third of the interval, they have to have the same sign. Here's what they proved. They solved the case of 3. And they showed that, I mean, they adapted our proof that what they showed is if you have 3 cosines, they all have to have the same sign on at least a ninth of the interval. And the extremal case is if the frequencies are 1, 3, and 9. And of course, all multiples thereof, right? I mean, if you take 10 and 30 and 90, that's just 10 times the original question. Okay, 1, 3, 9. And here's what it looks like. And you see it's kind of a nice recursive thing. And then, well, okay, I'm going to tell you about the proof. The proof is kind of, it's essentially our original argument with a little bit extra, because what happens is if C is a lot larger than B, it should like cut it in half, right? You should lose a factor of a half, but the answer is a ninth. A ninth is 3 times 3. If you lose only a half twice, it's only a quarter. So the very fact that this number is quite small forces implicitly a form of compactness, because if C is infinitely larger than B, right, then B looks a little bit like this. And then C is going to come. I mean, we already know that A and B coincide on a third of the interval anyway. C is going to look like this, right? And it's going to select half the interval automatically. So that's a factor of 1/2. So that what gives us a 6, right? It gives us a third times a half is a sixth. But the fact that this is not happening, that the answer is a ninth, implicitly forces a form of compactness. I think this I kind of say here. So basically, you can kind of show that B cannot be much larger than A, C cannot be much larger than B, and then you can use the computer to exclude 1,000 cases. It's not the proof that you can teach. It's not a proof that really explains why, and it's not a proof that generalizes. So if you want to do this for 4, this proof would not work. The computational complexity is just, the way it was set up here just doesn't work. Okay, but it turns out they also proved the following pre-result, right? Very nice. They said, oh, the answer is decaying at least exponentially, and it's not 1/2 to the n, which is what you'd expect if you take large random numbers. But it turns out by taking powers of 3, you get 1/3 to the n. So we have this beautiful, and this is a proof by induction that's very easy to do because the set is very self-similar. Okay, so the answer is 1, and then it's 1, 3, and then it's 1, 3, 9. Of course, the next one is 1, 3, 9, 27, right? Except it's not. So this is not known. But the extremal examples of the frequencies are you have 1, that's just 1, then you have 1, 3, you have 1, 3, 9, and then we don't know. But for n equals 4, maybe the worst case is 1, 3, 11, 33. And for 5, it's maybe 1, 3, 11, 35, 105. So what is the sequence of numbers? I have absolutely no idea. There is one very slick argument by Lars Becker that he told me about last week. And that argument is here. So it turns out it's at least 1 over 4 to the n. And he was reading Emmanuel's papers. That will show up in the proof. So what he's doing is replacing the cosine. And he's just, instead of asking, what's happening with the cosine, he just takes the indicator function and says, when are they all positive? He's proving a lower bound on something smaller, right? He says, when are all the cosines positive? They're all positive if you're between minus pi over 4, pi over 4. Okay. Or pi over 2, right? Maybe there's a 2 pi missing here somewhere. Then he takes a very nice, suitably chosen function that is positive definite and bounded from above by this bump function. He uses that as a lower bound. He uses positive definiteness to get the power, and then he's optimizing over phi. And he picks this phi. And he tells me that the papers of Emmanuel indicate that this is the optimal phi. Maybe Emmanuel can weigh in, but that gives you 1 over 4 to the n. So now we have an asymptotic counting problem, and it's between 1 over 3 to the n and 1 over 4 to the n. Now, I set this up nicely, didn't I? Someone said 4. What's the nicest number between 3 and 4? Right, it's probably pi, but pi doesn't match. So pi to the 5 is not quite 100. It doesn't quite work. It seems to be a bit larger than this. Something strange is happening. I don't know what's going on. If you have any, this is a very, for people who want additional motivation besides, how weird, you could think of this as a measure version of the lonely runner problem. For people who know this, lonely runner problem. It's n particles that move at unit speed on a circular track. Each one of them gets isolated. This is kind of a version where you ask how often are they all on the same side of the track. And it sounds like elementary Fourier analysis, but it's not clear to me how elementary that is. And with this, I think it's 10:50. I'll finish right on time, and the next problem follows on Wednesday.